Okay, here I am in front of my computer. I have Xfoil up and running, and I have a NACA 23012 airfoil plotted here. It's at a 60-degree angle of attack, and it's running at a Reynolds number of 500,000. And we see the pressure lines on here, and we see the pressure distribution. And before I go any further walking you through this graphic, the reason we're here doing this, it's all Peter's fault. Partially Bob's fault too. Because as I talked through what I've already mentioned to you in the video about the flat plate trailing edge flap being the probably the only control surface for this type of aircraft that actually works properly, free of flow problems other than spoilers. Um, and as I talked Peter and Bob through that, and they says, well, your arguments are logical, makes sense. And Bob had a good technical explanation concerning the pressure gradient. And Peter had a nice layman's explanation, even though he's just as smart as Bob and can talk through the technical stuff. But I appreciate Peter's comment because it's something I'm going to use to explain this whole phenomena to you, my viewers. Um, and so that was a little gift from Peter. But the big bugaboo is they're like, okay, it's all very logical and it makes sense when you say it, but prove it. What is it that happens with the flow? What's going on in terms of the fluid dynamics that makes standard control surfaces not work? And I went, oh, I knew you were going to ask me that because that's the same question I've been asking myself for the last 3 nights as I toss and turn in bed, you know? And only a really smart person like Bob would ask that question. And I think I'm almost as smart as Bob, so I've been asking myself the same question. Actually, any good engineer will sit there and say, oh yeah, it makes perfect sense, but prove it. So here we are with Xfoil moving forward, and I'm going to do a series of experiments and runs here and attempt to prove my conjecture that the flat plate trailing edge flap is the only way to go for low speed foot launchable glider aircraft, especially on flying wings. So here we go. Let's talk about, if you haven't used Xfoil before or haven't studied airfoils much, you might not be familiar with these curves. So first of all, most important thing, remember that these curves are plotted inverse. It is negative going up and positive going down. And of course, we plot them that way so that we're not having to think upside down all the time. You know, that negative is good, it's lift. So this is the lift that's going on here. And any forces going out on the lower surface are counterbalancing the forces that are going out on the upper surface. And one of the dandy things about the 23012 is that the leading edge, even on the lower surface, it's generating lift. They did some tricky stuff on how they shaped that. And you get a lot of lift way up at the nose, and that's what helps keep the pitching moment curve so nice and flat around zero and gives us essentially a zero pitching moment curve, which is peachy for flying wings. We don't want a big nose down pitching moment. And they did that very efficiently by how they shaped the leading edge of this airfoil. And out of the NACA databases, this is one of the most efficient airfoils that you'll find in there in terms of L over D. It's not the best, but it is one heck of a good compromise. And even if you're doing a conventional configuration, this allows you to keep the smallest horizontal tail possible because you're not having to counteract a lot of nose down pitching moment. Okay, so that said about the 23012. This is the airfoil I use out at the tip of my wing. So lower pressures on top, negative, positive pressures down. And we see those pressures plotted here. And the longer the arrow, the lower the pressure. And if you had a series of pressure ports in here and a bank of manometer tubes like we used to have back in the day in college, this is what you would see on your manometer board. You would literally see this pressure distribution. And this chink in the curve here, I can't say for certain, but I believe that this is where the program is demanding that the boundary layer go from laminar to turbulent. So you see, boom, big drop there. And any place where the pressures are increasing, i.e. these arrows are getting shorter, so don't confuse shorter with decreasing. The magnitude of the low pressure is decreasing, but we call that an adverse pressure gradient. Anytime that we're going from low pressure to high pressure, back here at the trailing edge, that is an adverse pressure gradient. Where we're going from high pressure to low pressure up here on the leading edge, that is a proverse pressure gradient. And we name them that way for a reason, because as the poor little air molecules get shoved over this airfoil, we get them accelerated here in the front. You know, they come in at one speed, 20, 23 miles an hour, and then we speed them up by making them go uphill, and because of Bernoulli and its incompressible flow, they have to go faster, and the pressures drop, and we get lift, the magical lift that we're looking for to fly. But eventually we have to pay the piper, and we have to give it all back. And we have to get that flow back to free stream conditions in terms of speed and pressure. So the pressure going off the trailing edge here has to be essentially the same as what came in at the leading edge. If it's not, you get a bunch of turbulence off the back end of the airfoil. So adverse pressure gradient, the pressures are increasing. Anytime there's more pressure in front of you than behind you, that makes it hard to move forward. And so it's true for air molecules. They're trying to move down the airfoil here. They're moving into a higher pressure region, and they'd prefer not to go, but they got two things pushing them along. Their inertia, we sped them up front here. They have higher velocity, and air molecules have mass, so they have inertia, and then inertia is going to carry them through this, so they're trading off speed for distance as they go through the adverse pressure gradient. They're losing velocity but continuing to move forward, so their inertia is going down, 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 and it's incompressible flow. They have no choice. There's a bunch of molecules behind them, and it's either keep moving or get out of the way. And one way that they can get out of the way is separate and go off somewhere else, and then make room for more molecules coming in behind them. And that would be like in a stall. And the flow would be all confused and very draggy, and we don't like that. The other thing is that they can turn left or right, go inboard or outboard. Well, on a tapered swept flying wing, going inboard is difficult because of what the flow conditions are like, but going outboard is quite easy. And that's why we have span-wise flow on swept wings. The flow is trying to find the easier way out, and that would be span-wise. And in fact, if the conditions are bad enough, as we've seen on my my wing when we were out with the initial tests, and I'll put up a picture here so you can see that, they literally turn 90 degrees, turn the corner, and head out to the wingtip. In fact, the first time we saw that, it's like, holy smokers, how is it that flow that was going this way can, in such a very short distance, turn 90 degrees and head straight out to the tip? And that really sucks, and we got a problem. As we searched through that problem, we were barking up a lot of wrong trees. And only recently have I begun to understand what's actually going on, and I'm going to talk about that in a little bit here. So there's the basics of airfoil analysis and the things that we can look at in this program, and Xfoil is pretty darn close to reality for lower angles of attack, anything below 10 degrees. You go in and run this in a wind tunnel, you're going to get the same results. Okay, so next I'm going to take a moment here to set a 20-degree flap on here, and we're going to take a look at the pressure distribution for that. And as we close out this segment, I'll just animate it through its angles of attack, and you can see how the pressure distribution changes as we go through those angles of attack. And let me stop it here for a moment and mention one other thing. Right back here, you'll notice that there's a swap in pressure distribution. Here it's out, away from the airfoil surface, and here it's down towards the airfoil surface. In other words, these are positive pressures, these are negative pressures. And why does this is going to come into great play here in a few minutes. But why do they swap right here? Well, there's a little bit of reflex in the mean camber line of this airfoil. The designers of this airfoil are trying to get the flow back to on the chord line so that the flow exits the trailing edge as neatly and cleanly as possible with the least amount of drag. And this just this ever so minor amount of reflex helps greatly with the keeping the neutral pitching moment curve. So we'll reanimate one more time. We'll step through this. High lift near stall, and you'll see that that pressure reversal at the trailing edge comes and goes depending upon the angle of attack. That was fun. Okay, so we'll be back in a minute to look at the flap condition. Okay, we're back. What I have here is the same airfoil, the 23012. I've moved it further up on the graph so that we can see certain features that I want to discuss in a moment here. We're still flying at a 6-degree angle of attack, Reynolds number 500,000, but we have 20% of the chord. In other words, the hinge line is at 80% of chord, so 20% is back here as a flap, which is the control surface, and in our particular case with flying wing, the elevon. And the way that Xfoil sets these up, the hinge, you can set the hinge line so that it's right in the middle here, and that's analogous to what I have on my wing in terms of the ball and socket joint, that it's not hinged on the upper surface, not on the lower surface, but right in the middle, which is traditional for general aviation aircraft. It's a nice, efficient configuration and generally disrupts the flow the least amount. It's also one of the more complicated ones to build. So it's a trade-off. So we got the same data here, the pressure distribution on the airfoil, and then the plot of that pressure distribution. And we note that you can't see it here, it's off the screen, but these pressure vector arrows are much taller. We're generating much more lift up front, and we have all of the arrows are taller back here, so the adverse pressure gradient slope is about the same, but it's a little bit more spread out. And we note that we have this set of pressure vectors here which have a significant spike in them. And that's represented by what the curve does here. Our adverse pressure gradient is here. The pressure is increasing, increasing, increasing. Velocity is decreasing. And then that begins to flatten out. And then all of a sudden, the pressure drops more. And then boom, big recovery and back. So there's a lot going on here at the trailing edge where the hinge is. And you can look at this in one simple way. If this chunk of the airfoil, if the control surface chunk were not attached to anything else up front, well, that'd just be a symmetrical airfoil with a round nose on it flying at a 20-degree angle of attack. So it's going to generate a lot of lift right at the front of that airfoil. So it's essentially we have an airfoil strapped down to the back end of our airfoil, and when we deflect it, it generates a lot of lift back here at its leading edge, and that's what gives us the nose down pitching moment. We're adding lift back here. We've got a force pulling up on the back end of the airfoil, and that pushes the front end down, which is what we want. We give down elevator, we want that nose to go down. Likewise, if it's an aileron function, we get a nose down pitching moment, but we also get a tremendous rolling moment because it's out at the tip, and we're generating a bunch more lift up front here. And all of that lift is trying to lift up the wing and make you roll. And if this were the left wing, that would make you want to roll to the right. Okay, we're not showing drag or anything here. We're ignoring that for the time being because it's not germane to our discussion. Now you remember we talked about the poor molecules having to beat their way into this adverse pressure gradient. Well, here it's a little bit better because we sped them up even more up front, the flow here on the leading edge of the wing is even faster. So those molecules have a little bit more inertia to get through this pressure gradient. So they're going along, doop, 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 doop. We're doing the job. We're going into the adverse pressure gradient. They're losing velocity, but they're going, I'll make it. Don't worry. I'll get back to my nominal conditions. And then bam, they run into a wall. Literally, we've created a wall here for them. You can't see it. That's why it's not the first thing we thought of when we had problems. But by having this type of control surface, you build a pressure wall here. This adverse pressure gradient here is tremendous. And it's way back where a lot of the energy that was in the boundary layer has already been spent beating its way into the adverse pressure gradient. So made it really hard here all of a sudden. This is analogous to, I think, a good analogy for this. You know, started many football games. You got the team runs out onto the field, and the cute little cheerleaders got that nice paper banner up, you know, and the big tough guys burst their way through the paper banner, and ta-da, we're ready to play the game. Well, this is somewhat similar. If I had a heavy sheet of paper there, and my football players were walking very slowly instead of running or trotting, when they got to the end, the cheerleaders are heavy and a lot of them, they hold that paper tight. And when the football players get there, they're just going to all pile up against that paper because they're just walking really slow. They don't have any inertia. All they have is just their basic mass, which is holding them down to the ground. And then they got more football players behind them. And if they're incompressible flow, if we treat them like incompressible flow, the guys that got there first to that banner, well, they got to get out of the way because they got more guys coming behind them. And the banner's holding. They got to go somewhere. So they go sideways. That's the only way they can go. And that's essentially what we've done here. We put up a barrier to the flow that's going very slow at this point, relatively speaking. And it just can't get through this pressure gradient. So it goes out along the banner, which in this case is our wing. It turns a 90-degree corner. We've seen that picture. The toughs, oh, we're going straight back, and then boom, out along the wing. This is why. It ran into a wall, and it can't get through that wall. So all it can do, because it's not moving fast enough, there's not enough inertia, so it goes out along the wing. General aviation, that flow's going 50 miles an hour, 60, 70, 80, 100 miles an hour, no problem. Turbulent boundary layer, lots of velocity to spare, a lot of energy in the flow. Boom, right through that barrier. It's just like the running football players, and they just go bam, right through that paper barrier like it's not even there. And that's what happens with the air molecules here. Now, sometimes we can work around this problem by turbulating the flow and pulling energy out of the free stream and put it in the boundary layer as a turbulent boundary layer and help it get through this barrier. And when I went out and tested the various trip strips, I found that the vortex generators helped a little bit. But we have to remember, we're starting out with really slow flow to start with, only 20 miles an hour. And the mass of the air is the mass of the air. We can't change that much. So it's only got a certain amount of energy, and we've spent most of it by the time we get back here. So it still has a hard time getting through here. And that's why trip strips back here along the hinge line don't work for me. They work on sailplanes, but not for me, because my flow is going like just a skosh over 20 miles an hour. And on a sailplane, it's doing 50, 45, 50 miles an hour. Much more energy can go through this barrier. Or you can put little trip strips there, and you have enough energy in the flow that it turbulates it, and then you pick up more energy out of the free stream, and you keep the flow attached on your control surface. I do not have that luxury here because we're flying both slow, got a thick airfoil, and a big round leading edge on our flap. So you get messed up flow. And when you see that, when Peter and I first saw it, that's why when Peter said, oh, flow through the gap. There's a hinge gap, high pressure on the bottom, low pressure on the top. Classic theory, we've all been taught in school. Flow's going through the gap and causing separation, and it's going out along the wing. And I went, yeah, you're probably right, you know, because it's a classic explanation of it. But when we sealed that gap, it wasn't vastly improved. It wasn't like the problem magically went away. This is why. we probably weren't having very much flow through that gap because the flow speed's very slow and the pressure differentials are relatively minor. What we had was a wall, and the flow couldn't get through the wall, couldn't go over the wall, so it just went out along the wing. 90-degree corner, an amazing thing to see. You know, as an aerodynamicist, it's not every day you see flow going one direction, then just take a hard left or a hard right, 90 degrees, and go the other way. But this would cause that. And when you're standing there trying to visualize the flow, there's many things you visualize, but you don't visualize this hump in the pressure distribution, this drastic increase in adverse pressure gradient. And then as I talked through this whole thing with Peter, he says, when we were talking through this, we weren't even really, Bob was talking about this pressure differential stuff, pressure gradient. But as Peter and I talked through this, he gave me the wonderful layman's explanation of this, or in addition to this explanation that's really would be for lay people, that's easy to understand. The flow's coming along here on the surface, and it has very little energy in it, and then you ask it to turn a corner. It's got to turn this corner and follow this surface. And turning corners takes energy, and there's not much energy in there. So it's kind of a double whammy. You got an adverse pressure gradient, and you got to turn a corner, and the flow has no inertia left in it. So this is why when I moved my hinge line way up here near the spar on my wingtips, then it actually worked out okay. If you're close to the maximum thickness point, you have much more inertia in the flow, and it can get through the adverse pressure gradient, and it can get around the corner and stay attached to the wing and make it through the rest of the adverse pressure gradient. However, it's not plausible to hinge the elevon at the spar along the entire length of the elevon. It'd be so heavy, and you have flutter problems, and you can't counterbalance. It just goes on and on and on. It's just a mess. The Horton brothers, who are a couple of smart dudes, we'll have to ignore the fact for the moment that they were beholden to the Nazi regime, but they were still smart aeronautical engineers, and they tried to deal with this problem when they went to Argentina. And like us, they were more fascinated with gliders, and they had the concept of, I'm going to build a flying wing just sized for me, and I'm going to run off the side of a mountain and fly around. And it's just like the birds, you know, and for those of us who love to fly, it's a very attractive scenario. So even the Horton brothers worked on a foot-launched rigid wing sailplane, and I'll put up a picture of it here. And we'll see that the elevons are actually hinged at the spar. And the elevons have almost no span to them, but lots of chord. So you can see that they were dealing with this problem also, because as a hang glider, it's inconvenient and heavy to create a second spar like I did for my elevons somewhere in the middle of the wing. It's just easier to say, I'm just going to hinge it to the spar and be done with it, which is what the Horton brothers did. And then I don't need as much span to get these short span elevons on here. And if we take a look at another view of their glider, you see giant wing fences. They're really tall. So that tells me right away that they're dealing with a horrible span-wise flow problem. And they did the classic solution. They slammed on some wing fences to try to fix it. Well, this aircraft that they worked on never really flew well. And it turned out to not be foot launchable. They had to tow it. They might have had a couple of short hops, and it became a hangar queen. And that's because at that point, they had failed to understand or hadn't reached the conclusion, and it took me decades to get there. The span-wise flow problem is not a boundary layer problem. It is a potential flow field problem. And fences do not fix a potential flow field problem because they're too short. Fences fix boundary layer problems. But the span-wise flow is not a boundary layer problem, so you put a fence on there, nothing happens. You still got problems. You put a taller fence on there and a taller, and you're just until that fence becomes a significant percentage of the half span of the aircraft, because then you're dealing with the potential flow field. And in my particular case, that's like at least 3 feet tall. And these fences that we see on this glider are nowhere near a significant percentage of the span-wise, of the half span. So they're trying to fix a problem and failing. And it's because they hadn't wrap their brains around. They're not dealing with a boundary layer problem, they're dealing with a potential flow field problem. So here we are. We have evidence here that this classic setup for hinging control surfaces for low-speed aircraft, foot-launchable aircraft, a bad plan, because you create a flow, you create a pressure environment that the flow has a hard time getting through, and you get separated flow, premature stall, laminar separation bubbles, all kinds of problems. And now we're about to understand why the flat plate flap back here instead of this thick thing actually works, even though it's less effective. It doesn't generate as much lift at its leading edge, so you don't get as much nose down pitching moment, but we can make up for that by making the chord of that flap a little bit larger. But it solves the problem in terms of this pressure distribution, creating a wall here. If we don't create this wall and we get a turbulent boundary layer, we'll get through that adverse pressure gradient. We'll get off the trailing edge gracefully without going spanwise. And that's what I'm going to begin to show you in the next segment. Okay, here we are. Here's the NACA 23012 airfoil, which I've scaled down to 80%, right here, 80%, with a flat flap on the back. Very interesting. We see the flow conditions or the pressure distribution is the same as the standard 23012 all the way back to the trailing edge. We have the funny little reversal right here where we have a little bit of reflex in the airfoil. Pressure distribution is the same, and nothing happening back here on the flat plate except for some skin friction drag, and then right at the end of the flat plate we have two more pressure indicators here, and that's because the plate does have some thickness and the flow has to get around that sharp corner and get back to zero by the end of it. But there's essentially nothing happening here other than the flow cruising along at very, very close to the free stream velocity, because we've gone all the way through the adverse pressure gradient, and we're here at nominal free stream flow conditions at the trailing edge of the airfoil, yet we still have this flat plate to go along, and it does that quite easily. So that's how it looks with just normal flight, and the controls are in neutral, nominally neutral. And we see here on the pressure distribution that it doesn't quite go flat because we're at an angle of attack and this is a flat plate back here. It's generating a little bit of lift, so there's some pressure available here that causes this to have a slight slope to it rather than being absolutely flat and nothing's going on. So there's a little bit going on back there, mostly driven by what's happening here at the trailing edge. So nominally, no impact on the basic performance parameters of the airfoil. If we go over here, we haven't looked at these before, but this is CL over CD. This is the coefficient of lift versus the angle of attack, and this is the pitching moment. Now, the biggest change by putting that flat plate back there is on the pitching moment curve. This curve is usually, if I were to compare it, I'm going to try to do that here in a minute, call in the regular airfoil and compare them, you'll see that the pitching moment curve is a little bit more nose down because of the flat plate that's back there. And I'm going to talk here in a moment about how we're going to eliminate that also and get to, it's not bad, you know, you could just pull in a little up elevator and correct for that pitching moment change. But overall, the performance of this airfoil is the same. That flat plate does not do much, changes the stall angle of attack a little bit. Let's see if I can gracefully do that here and try to add in that the standard 23012 airfoil, if I can do that without screwing up here. Should be that one. And now we have to go turn them on. We have to go back and reanalyze here. We need to do a batch analysis, call that up, do an analyze, wait for it to chunk through both airfoils. completed. Go back here. Now we see both of them. And let me see, I'll change this one to a different color so we know who we're talking about. We'll make him a bright green. Okay, so the bright green one is the standard 23012 airfoil, and the dark green one up here is with the flat plate flap on the back. And you see that the nominal airfoil has a slight nose down pitching moment here, and the other one has a slight nose up pitching moment, and which is slightly greater than this difference here. So that's of note. And we notice here that the standard 23012 has a steeper lift curve slope here, coming up to about 5 degrees and all the way up to about 10, and then they're back to about the same for the two airfoils. So the 23012 has a better lift curve over most of your flight regime. In other words, it doesn't generate quite as much lift as the standard 23012. And how would we correct for that? Maybe a little bit more wing area, but it's not a huge deal. So there's some minor changes, but essentially the same characteristics. I mean, if I put a regular cambered airfoil in here, this pitching moment curve would be way up here off of this particular chart. You'd have a big nose down pitching moment. You'd need lots of washout. So I haven't completely ruined the pitch characteristics of this airfoil by tacking on that plate on the back. Okay, I'm experiencing the same results that I received last night when I was running through this stuff, is that when you deflect the flat plate elevon on this airfoil, Xfoil program has a hard time calculating through some of those angle of attack ranges. It's where we saw the little burble in the lift curve slope. Where that burble occurs, the program doesn't actually complete the calculations, and it goes from having a solution at 2-degree angle of attack and a solution at 11-degree angle of attack. So I'm presenting the 11-degree angle of attack here because, you know, at least it's a positive angle of attack, and I don't know which is worse compared to the 6, but we'll look at this one because it shows the phenomena which I want to point out to you. Here we are, we look at the hinge point of that flap at the trailing edge, and we notice we don't have that wall of adverse pressure gradient here getting in the way. We don't have a big spike in the pressures back here. We don't have a big drop in pressure at the leading edge of the flap, which caused the wall to form and make it hard for the flow to go forward here. And that's a big benefit. You have very little inertia left here, and what we've done is we've let the flow finish getting through the adverse pressure gradient and back to almost free stream conditions, and then we turn the corner. Because otherwise we're asking it to get through a nasty adverse pressure gradient and turn the corner. It is just too much to ask, and the flow goes off somewhere else. Here, it's got a better chance of having some energy in it. It has the free stream velocity, and it'll get around that corner and go down the flat plate. Now, this has probably got, because it's a flat plate, depending on what speed you're at, you could have a fairly thick boundary layer here, and it's bound to be a little bit draggy. But if we made this flat plate not quite flat, but a very thin triangle, and that's where we come into the, hey, remember where the flow, or excuse me, where the pressures were reversed on this airfoil, and it was forward about 10%? Actually, we're going to go look at a case where that's where we put the hinge line, and see what happens then. It might be even more interesting that if we design a essentially flat plate, and that's kind of what I had on my original wing. My original wing had, and I'll put up a picture of me ground testing it here, it had 6-inch wide elevons. They were about 7 feet long, and at the front they were 3/4 of an inch thick, and at the trailing edge they were, you know, a 1/16 of an inch thick. And the reason that they were 3/4 of an inch thick at the front was for structural considerations, and it also matched up with the trailing edge of the ribs, which you'll see in another segment as a part of this video. You'll see that the ribs have a certain minimum height at the trailing edge because of how they were made, and I just made the elevon match that, so I would match up with the outer surfaces of the airfoil at that point. So I ended up with a triangular shaped flat, essentially flat plate elevon, and they were fantastic control system. And you ask, why didn't I keep that here? Well, this flow conditions weren't fully understood in my mind, and I built a hinge type that is traditional in general aviation as being a high performance type hinge, and I wanted high performance. This control method with a flat plate, not as efficient, but effective. Those are two different things. One's associated with a lot of drag and reduced lift, and the other one has to do with, are you getting pitching moment? Are you keeping the flow attached? Are you doing the job you're supposed to do in controlling the aircraft? And the answer for flat plate is yes. And so we have 6 aircraft designs that have arrived at this conclusion, not by understanding the aerodynamics, but by meeting the demands of transportability. Because we want them to be transportable, we have to take the elevons off or fold them up somehow. We ended up with essentially flat plate elevons that are tacked onto the trailing edge of an airfoil. And that turns out to be the workable answer. And nobody else has tried, as far as I know, a foot launch aircraft with elevons with the bull nose leading edge and tried to foot launch it and fly it down at really low velocities. I think the Pranal M, which we know had reverse taper elevons way out at the tip, and they were, I believe, a bull nose type elevon situation, and that flew fine at El Mirage, but it was under tow, and from having watched that video, I would say they never get down around 20 miles an hour. They're probably flying 30 miles an hour, 35 miles an hour, maybe more. And then you're up at a Reynolds number and a speed that gives the flow enough inertia to get through those adverse pressure gradient barriers. And they never experienced the problem. Now, could we do that with my aircraft? Yes, but then it's not foot launchable unless you got a 25 mile an hour headwind. And you can only fly in stormy conditions, which we don't want to go up in anyway. So it doesn't answer the objective of being foot launchable. So the other aircraft that have worked with these flat flaps would be the Stalker, the Impact, my original wing, and the Millennium. And you're going to see here in a bit that even though the Swift cut their elevons out of the wing, as opposed to just tacking them on the trailing edge of the airfoil, they essentially had the same scenario set up. And I'm going to go and explain that here in a minute, but it's fascinating to see. And I suspect that despite all the PhDs at Stanford, it wasn't something that they thought through. They picked an airfoil that was appropriate for their type of flying, and then they just cut out the size elevons that they needed for control effectiveness without giving thought to this phenomena, because this phenomena only occurs in a very narrow region of Reynolds numbers and speeds, and it's quite easy to accidentally sidestep it and not know a thing about it. And I'm the guy who happened to put his foot squarely in that area and had problems and had to go to the point of understanding what's going on. Or as my buddy Bob says, what's actually happening with the flow? Explain it, Raul. Well, here, I've explained it. And you can actually see it visually, thanks to the wonderful program Xflr. And I'll take a little aside here to do a shout out to an old buddy of mine, Guppy Youngren. And for those of you in the aviation community and in the know, you know who Guppy is. He's one of those super smart guys that came out of MIT. I hope he's still out there somewhere. And I wanted to send him a shout out of great thanks, because he's one of the creators of Xfoil in the early days, when our computers didn't have enough power to do all this, and it had to be run on a mainframe, and they had to finagle their way through it. They were really on the cutting edge of developing this code, and he and several others developed Xflr, and then it just grew and grew. And now it's a tool that's used worldwide, universities everywhere, great teaching tool. Guppy, thanks much for your contributions to the aviation community. They're almost immeasurable. And to finish the story, I'll tell you, his real name is Harold, and you'll see technical papers out there by Harold Youngren. And those who know him as Guppy. And he got that nickname when he was a little baby in his crib, and he used to flip around a lot in the crib. And his parents nicknamed him Guppy because he flipped around like a fish. So there, you have a little bit of aviation history there. And now we'll move on to the remaining parts of my story. Okay, I wanted to take a moment here and show you one other flat deflection for this type of control surface, the flat plate. That is 10 degrees. And I find it to be fascinating. First of all, the program can actually handle doing the calculations for this funky airfoil when the flap isn't deflected as much. And you'll see that we still don't, at 10 degrees of deflection, there's no adverse pressure gradient barrier here. It's very easy for the flow to just continue on its way. In fact, I'm going to turn off the pressure indicators here. There, they're off. And what we see is the flap is now kind of aligned with the aft surface of the airfoil. So even though at this point we've deflected the flap down 10 degrees and we're getting a nose down pitching moment, we're not asking the air to turn a corner here. We've gone from a concave to a flat scenario. The way to look at this in a better way mathematically is to say that locally the first derivative is continuous here. There's no kink in the curve. It's flat. And any time where you have flow of just about any type, whether it be air, water, something else, electricity maybe, I don't know. If the first derivative is continuous everywhere, then the flow will be continuous. It will be smooth. And that is an interesting phenomena that occurs here. When you hinge up here in this area, well, you don't have that effect. As soon as you deflect it, you're putting a kink in the curve and thereby putting a discontinuity in the first derivative. Back here, you've taken the kink out and you now have this nice smooth curve with no discontinuities, and you'll have very well behaved flow, most likely. And generally you can say that in many areas of physics, you keep that first derivative continuous, no discontinuities in it, and you'll get much better behavior of the other physical phenomena that are occurring on that surface. So that just a little aside there that I find to be interesting. I'm going to turn the pressures back on here. We'll let the animation run. You can watch this go through its deal here, because with this 10-degree deflection, we can run through this, and it has enough solutions so we see that we never develop that pressure spike at the leading edge, yet we are getting a nose down pitching moment. We'll go look at that curve in a minute. It's not as strong as it is if you have a nice thick trailing edge flap, but we eliminated the other problem. So, fascinating. Okay, let's stop this and we'll go take a look at the other curves, the performance curves. Let's go over to those. So now what we see here are 4 curves. We have the airfoils that we've been looking at here. The lightest green one here, this one right through here, this is the standard pitching moment curve for the standard 23012. And you see that at 0-degree angle of attack, the pitching moment curve is pretty close to 0. It's a nice neutral pitch stability on it, and it stays pretty close to 0 over a wide range of until you get up here near stall. And its drag bucket here, the light green here, not too bad. Pretty nice. This airfoil has a high L over D. Okay, and then we have this next one here, if I can call up and get the name on them. Where is the name on that one? I've lost track of them. Maybe I can get this to slide over. No, I can't. Let's see. Let's turn that one off. That's the baseline. No, we'll leave the baseline turned on. Turn that one off. Turn that one off. I think this is the most recent one I did here. This has the this has the 10-degree deflection. So this is the difference in performance with the 10-degree deflection. Of course, we have a much higher CL that we're generating with that airfoil with a flat plate deflected 10 degrees, but not that much more drag. The peak drag went from, back in here to just over here. And not only that, up for fairly high coefficients of lift, up to 1.2, they're the same. So you can deflect that flap on the trailing edge 10 degrees and go all the way to a CL of 1.2 and not have affected the L/D performance of the aircraft. That's pretty cool. You can put that flap down 10 degrees and pick up speed and not have ruined your performance with the flap. That is not true of thick trailing edge flaps. This light green, this brown curve would actually be moved over in front of the light green one here, and you'd actually have more drag over a wide range. So this is the one with undeflected. This is the undeflected flat flap compared to the baseline 23012, and we see there's not much difference in the L/D curves. In fact, here at real high CLs, it actually pulls more CL per CD at very high angles of attack near stall. So at stall, it actually performs a little bit better. Turn that one off, turn this one on. This is with the flat plate deflected 20 degrees, and we have a kink in the data here because the program was having a hard time calculating through it. And we're pulling a lot of CL, but the CD is also much higher. We moved from over here to way over here. How valid this data is, I don't know, because the program had a hard time calculating. And we see that, of course, we have a big nose down pitchy moment because we have a big flap deflected down, way down. And this is the 10-degree one. The 10-degree in terms of, let's see what the numbers are. Here's about 0.08. And let's turn this one back on. So here's 10-degree deflection. Here's 20-degree deflection. So doubling the deflection in the elevon doubles the nose down pitchy moment. And that's about what we'd expect, unless we have separated flow or other problems. So adding the flat plate on the trailing edge of the airfoil really doesn't destroy its performance much. And these are the kind of stalls that we would expect, right? As we deflect the flap down in the rear, we're decreasing the stall angle of attack. However, that's okay because we're putting the nose down anyway. You put that flap down, the nose goes down, and you're going away from higher angles of attack, so it's fine. And for the first 10 degrees, you have the same lift curve slope here. And with the 20-degree deflection, well, you have a much lower lift curve slope, as you would expect. So interesting stuff to look at, and interesting results with a very unconventional control surface that's been used on 5 or 6 different aircraft successfully that are foot launched of a certain size and fly at certain Reynolds numbers. Fascinating. And turns out to be the correct solution for those aircraft, and the standard way to design is wrong for these types of aircraft. You need to do it this way. And now, of course, we've talked about the Swift, and I'm sure people are asking, yeah, Raul, but what about the Swift? Let's go look at the Swift. How did they actually get the Swift to work? Why does it work? It's just cut out of the airfoil like you would normally do. And it flies fine. It flies great. It's a great design. Well, there's a reason why it worked, and I'm not sure anybody's ever really thought about it, but we're going to talk about it now. Okay. Now, before we go and talk about pressure distributions and pitching moment curves and all that other stuff, let's take a look at the Swift airfoil. Now, darned if I could not find coordinates for the Swift airfoil. I don't know what they are, but I know what it looks like. And it looks a lot like this. And this airfoil is the MkII or the MkII M06-13-128.dat. That data is available from airfoiltools.com, which comes out of the University of Illinois database. Shout out to my alma mater there, and thanks for keeping those databases. It's been extremely helpful to many aero engineers. So you guys are doing great work. Keep it up. And this airfoil was created and made for some wind tunnel testing that they did on laminar separation bubbles. And you can find some reports online about that out of University of Illinois. I have a copy of one. And this is an type of airfoil that was popular in the late 70s and early 80s. And the design, as we got into numerical calculations, CFD, we'd say, oh, we can do a reverse design now. We can say, I want these flow conditions to exist. Show me what the airfoil looks like. And we started getting a bunch of airfoils like this. And this is similar to one that's on the Swift. And these airfoils generate really great CLs and low CDs. And they perform extremely well at low Reynolds numbers. They deliver this fantastic performance at low Reynolds numbers. So the folks, all the PhDs at Stanford, not being idiots, went, let's put a low Reynolds number airfoil on the Swift. And you go, oh, good. This is pretty close to what it is. And you'd be hard pressed to see the difference. I don't know. There's might be a little peakier up front here. I don't know, but it's very similar. And it's going to have similar pressure distribution to what they have on their wing. And what they do here is they're delaying the transition to a turbulent boundary layer. They're keeping laminar for as long as they can. And then they're doing the most rapid pressure recovery possible without causing separation to occur. So they trip the boundary layer, it goes turbulent, and we recover the pressure as fast as we can without having separation. Those are the criteria that are set in the programs that generate these airfoils. And it produces these interesting results. Now, they had the wonderful side effect of their maximum thickness point is moved way aft. So with their swept wing, and it all worked out great for running their horizontal spar. That if you took my airfoil and ran a horizontal spar at the same place that they have theirs, I'd have no thickness in the middle. It would be so thin it wouldn't be able to carry the loads. But theirs, at where they placed it, it's absolutely horizontal. They got a swept wing, but the thickness of that spar is constant, almost absolutely constant along the length of the spar. It's an ingenious solution. I don't know if they did that on purpose, thought about that ahead of time, but it sure did work out good. And there you go. So they got this airfoil. Now, why is this not the perfect answer? Raul, why don't you just use this airfoil on your wing? And I think I've mentioned this before. I want to go fast. Well, the Swift goes fast, yeah, for its era, 1985, 89, somewhere around in there. And hang gliders are loping around the sky at 35 miles an hour, 40 if they're really pushing it. And if somebody's going to do a loop, they might haul themselves all the way up to 55. If you're loopy, you don't care about drag. So the Swift comes along and says, I can do 45 miles an hour like nothing. And it does it. You watch a Swift on a ridge run against flex wings, and it'll leave them in the dust back then. Currently, like the Wills Wing T3 or something like that, will pretty much keep up with the Swift in terms of being able to fly fast with not a lot of added drag. However, I don't care about those numbers. I want to go 70 miles an hour, 80 miles an hour, 100 if I have to or want to. Well, you take this airfoil and you start going faster than about 45 miles an hour at the Reynolds numbers that we're operating at, and the flow is just going to go whoop, right off the back, and you're going to have separated flow, and you're going to have all this turbulence back here, and you got massive drag. This airfoil is not designed to go really fast. It's a floater, as we say in the sailplane business. And that's why over in Europe, when you fly the Aerooptrix against the Swift, on light days, the Swift wins because it's a good floater, and the Aerooptrix wins on heavy days because the Swift can't really speed up and catch up or stay up with the Areopteryx because it's got all the drag coming off from this rapid pressure recovery region. So everything's a compromise, and so this is why I didn't put a low Reynolds number airfoil on my wing. And I know that the 23012 just in general without deflected control surfaces does pretty good all the way down to 500,000 on the Reynolds number, and because I was a bonehead, I designed myself into a corner where the tip cord was 24 inches and I got myself down below 500,000. That was just we'll call it what it was, stupid. But here we are. So let me go do analysis on this, and let's look at their pressure distribution on this. We do a batch analysis on this. You always got to do them that way. It runs real rapid. We close out that, and then let's go look at its pressure distribution, and let's get it up to 6 degrees. We'll animate this. Up she comes. 4, 5, and 6. There we go. 6 degrees. And I'm going to move this guy up so you can see him a little bit better. Let's get him up in here. So here we are. There's the Swift flying at 6 degrees angle of attack. Oh, look. Just like the 23012, they have a pressure reversal somewhere back here at the 80% of chord. And you know what? You know where they're hinged? They're hinged right about here. Might be a little bit forward of that. They might be at, I don't think they're not up at 70%. They're somewhere back in this region where this pressure reversal occurs. And they're relatively thin back here. They chose a spot. They needed a certain amount of elevon area, and they only have a certain amount of span, and they got some flap on there. So they made the span of the elevons the maximum that they could, and then the chord of the elevon just drops out of that little calculation, and it says, oh, it needs to be about this big. And that just happens to be where this pressure reversal occurs, which, as we've seen, is very handy. Handy dandy. And we see there's no hump. Because this is a rooftop pressure recovery type airfoil, they're called that because this kind of looks like a rooftop here. And then you get to that where they trip the flow right here, and whoop, very rapid pressure recovery as fast as you can without separating the flow. And then it starts to go out pretty flat. And there's not much happening back here. The adverse pressure gradient beyond about 60% of chord is minimal at best. Sorry, didn't mean to move that over. So they're into a situation where, by happenstance, the back end of their airfoil looks like and behaves a lot like taking a 23012 and slapping a flat plate on the trailing edge. This is essentially a flat plate here. The pressure recovery is essentially finished. They have no more adverse pressure gradient for the flow to force its way through. So they don't get early separation of the flow. And everything stays nice and peachy. And I know from tough testing that the elevons on the Swift, you can deflect them down 17 degrees before you start getting any significant separation of flow. So that's why the Swift was able to put on, and they have a V-notch in here. They use a V-notch off the upper surface, and they have nice flow conditions even though they cut the elevon out of the airfoil rather than sticking on a flat plate like so many others have. And they solve their transportability issue by hinging on the upper surface. They disconnect the push rod, and the elevon flips over onto the top of the wing, which is peaches because you have this kind of bucketed area and the elevon fits right into that space, and you don't make the package any thicker, and it stores in the minimum amount of space possible. So overall, in terms of compromises, a brilliant design. And also because of the selection of the airfoil, probably, we'll say accidentally, just out of happenstance, avoids this problem of generating a big pressure spike here. And I'm going to show you that in a minute when I deflect this guy. And we're going to go take a look at that case. But in the meantime, let's just animate this and watch it go through its angles of attack and watch the pressure distribution and how it behaves as we go to high angles of attack. And then we come back. And as that pressure rooftop pressure recovery begins to develop, like there, that's where this airfoil gets really great performance. Tons of lift, lots of lift, with a minimum amount of drag to do the pressure recovery. And that's the nicety about designing airfoils in reverse. You can set a certain set of criteria, and then you'll get a shape that actually delivers that performance. Cool, huh? Yeah, gotta love aero theory and math, and when you get a powerful computer to actually work the problem in reverse. It's cool. Once again, thanks to the developers of Xfoil. So let's get set up to do the flap. Okay, so here we are. We're nearing the end of our story here. It's been a long one. Here is the stand-in Swift airfoil with their flap deployed down 15 degrees. And I selected a slightly different angle than the other studies because 15 degrees is pretty close to where flow starts to separate off the elevon on the Swift. It starts to separate about 17 degrees. So this would be just shy of where separation starts to occur. And darned if we don't see our answer right here. There is no significant adverse pressure gradient wall for the flow to get through. It's just a continuing adverse pressure gradient. Most of the work has already been done. The pressure's been mostly recovered, and there's no significant barrier for the flow to get through here. There is a bit of a corner to turn because we have a significant continuity change or significant kink in the continuity of the first derivative because it is the slope is going one way here, and then all of a sudden the slope changes the other way here, and so there is a bit of a corner to get around. But the pressures are very well behaved all the way back until we get to the very trailing edge, and that's exactly what it flies like. And it works. That's why this works. It's not a flat plate stuck on a trailing edge, but close to it because of how the pressure distributions occur on the airfoil naturally. So what's the best way to answer this problem, to design these gliders? Well, my current answer is almost flat plate. Because to do this, what we're looking at here, to have most of the pressure recovery done by the time you get to this hinge point, you have to have one of these rooftop pressure recovery type airfoils, which has this type of upper surface on it, and they're just inherently going to be very draggy at higher speeds because flow begins to separate. And the folks that designed the Swift knew that about this airfoil. They just never planned on going that fast. They didn't have any desire to. Nobody thought hang gliders should go 100 miles an hour. If you want to go 100 miles an hour, buy a sailplane. So, yeah, that's one avenue of thought. And right now, I'm thinking differently. I want to go fast. And I myself, I might not ever go fast on my wing. I might find some younger person who believes that they're immortal and they can go fast. And I'll stand on the ground and watch them, and I'll say, wow, look at them go. Anyway, so there's our basic answer. This is why the Swift works and why my current wing doesn't work. And it's amazing the things that you trip over. I don't think anybody's ever looked at this closely before, but now we have a clue, and I can go back to the 23012 and I can look at where that pressure reversal occurs near the trailing edge, do the little bit of reflex that's in there, and I can create a trailing edge flap that might be pretty close to optimum. And I think, I'm guessing ahead of time because I haven't actually done this yet, but just by happenstance, that's going to come out looking a lot like the elevons I had on my original wing, of all things, because of where it was hinged, how it was hinged, and how the elevon was built. And all of that was done for reasons other than aerodynamics. In fact, at the time that I was doing it, I thought, well, this is kind of crummy on the aerodynamics, but I'm going to eat it. That trouble, I'll eat the extra drag to get the transportability. But the fact of the matter was is I accidentally designed in the right answer unintentionally. So, and the other thing that I did on my original wing, I'll put back up a picture of my wing here. If you look closely, very closely, study the picture, you'll see that the elevon does not have any twist in it. It's in a portion of the wing that is highly twisted. There's about 3 degrees, 3.5 degrees of twist that occur in the wing from the root end of the elevon to the tip end of the elevon. The wing itself is twisted, no, 3.5 degrees. But the elevon is flat. And I did that because I'm lazy. And I just simply built the elevons flat on my bench and said, screw it. So at the tip end of my elevon, it lines up with the chord of the airfoil. But at the root end, it's actually angled up slightly. So this all had the effect of actually making it more efficient accidentally. And it looked funny, but it's really kind of what works out best, because as you begin to deflect the elevon down, at the root end of the elevon, the way that the flow conditions are, you're not really asking the flow to go around a corner until you've deflected the elevon down about 10 or 12 degrees. So you get a lot of deflection down without asking the flow to turn a corner. So it stays attached. And it happened to be hinged right about where that pressure swap occurs, once again, unintentionally. So, kind of an interesting solution. Now it had a drawback. They were like essentially strip elevons, which I've discussed way in the past, are bad in terms of the stall spin problem. So what I should have had on my original wing are essentially flat plate elevons that have a reverse taper to them. And where have we seen that before? Let me put up a picture of it here. It's the Millennium, designed by Steve Morris. And he pinched his ribs, brought them together in a pattern where they got essentially effectively thicker airfoil as you get out towards the tip, because he's pinching the ribs together, and he's tacking an elevon onto the trailing edge just like the rest of it because it's easy for transportation. And he ended up with this reverse taper elevon. And I sent him a message once and I asked him why he did it. He did not do it in terms of the stall spin problem, hadn't thought about that. He did it to reduce his induced drag by having the root end of the elevon have a smaller chord than the tip. And the way that it is integrated into the wing will very efficiently reduce the induced drag, which is exactly what you want to do for a flying wing. You want to get all of that induced drag as low as possible, and other drag. He's not peeling off a giant vortex at the root end of his elevon as if the elevon were just a big rectangular plate back there. You get a big rectangular plate, you get this giant vortex coming off the root end of the elevon every time you deflect it. So it was a very smart design, and as happens to many designers, there were other benefits that that design delivered that were unintentional and that the designer may have been unaware of when they did the design. It's the world of hang gliders. They're all developed experimentally. We make tweaks, we make designs, we go out, we test them. It doesn't work. We fix it a little bit, we fiddle around until it works, and we go, ta-da, this works. And then other people copy it and riff on it, modify and so forth. And nobody ever stops to do the hardcore engineering and analysis. Plus, we didn't have tools like Xfoil available then to find out what's actually going on with the flow. So very interesting. Now, I'm going to go away for a while, and I'm going to put out an entirely new and different segment of this type of analysis when I go back and do a little bit of optimization on the 23012 and how its flap is set up. And we'll see if that's really a superior setup. Okay, one more segment here. What I've done is I've taken the 23012 airfoil with the flat plate, quote unquote flat plate flap on it, and increased the leading edge thickness of that flap so that it matches the airfoil thickness slightly forward of its trailing edge. In other words, the way you can think of this, if I came in with a razor blade and lopped off part of my current trailing edge up to where we see that pressure reversal occur, and that would give me enough thickness on the elevon, it'd be a lot like my original wing where I have enough thickness there where I can put in some structure and keep it from being too floppy. What the Millennium did, the Millennium has carbon fiber top and bottom and a sandwich panel in the middle part of it, so the leading and trailing edges of its elevon are very thin, just a few layers of carbon fiber, and then I believe it's hinged to the sail either with sail material or sail tape. So on the bottom of the elevon, it's thicker, slightly aft of the hinge point to give it rigidity, and then by attaching it to the mainsail along its entire span of the elevon, the floppiness that it has inherently in it is removed, becomes stiff enough then. So, and that was obviously a very workable answer. That glider flies really nice. So what we see here is that at 6 degrees here, we're beginning to see some of the barrier develop here. It's a little one, it's not big. This is 15 degrees of deflection. Once you go to 20 degrees deflection on this, then that barrier is back to kind of fairly significant, and these pressure spikes here are much taller. And of course, it just says that as you give the flap portion some thickness up front, a more airfoil-like shape, it's more effective at generating nose-down pitching moment. But as we know, that's a problem in terms of adverse pressure gradient for the flow that's slowing up and trying to get around the corner. 15 degrees here appears to be about the maximum deflection without having a problem. And interestingly enough, that's about the same as what the Swift is right now. So what I'm thinking is for my next test, I'm going to take one of my wingtip panels, and I'm going to tack onto the back end a 1/2 inch thick piece of foam core board, and on the leading edge of the foam core board, I'm going to put on a half round radius leading edge. I'll just leave the trailing edge square, or I might taper it off, I don't know. And then I'm going to use duct tape to hold it to the trailing edge of the current wing. So I'll have about a 1/2 inch of thickness there. It'll stick up above and slightly below the current trailing edge. It'll protrude into the flow. And I'm actually going to take some pinking shears and cut some V-notches into the duct tape to see if we can trip the flow and get even more deflection. But it'll be very interesting to see what that setup is like. And I think with the current carbon fiber materials, that if I had a flap that's a 1/2 inch thick, I can probably successfully make it stiff enough to fly safely. So until then, this remains unknown as to how effectively I can solve the problem this way. But I think we're on the cusp. Worst comes to worst, we just make the leading edge of the flat elevon sharp and attach that to the trailing edge. I should probably make a version like that before I go. Make one with a sharp leading edge, one rounded, and we'll see how that goes. It'll be interesting. I would do it here in Xfoil, but creating those shapes in Xfoil, given the fact that it uses a .dat text file for the data, is problematic. So we'll just do the old-fashioned cut and try engineering. So wish me luck. Bye for now.